Let me start off with a problem. I have two computers, one in Florida and one in Albania. I want to communicate between the computers to send over a message. How do I do it? Now, before we answer this question, I need to mention protocols, since protocols are necessary to make any assumptions we can make later on. A protocol is a collection of instructions that, when implemented, achieve something, and they provide the ability to make even more protocols on top of them. Protocols are used to realize the chaotic potential of information into orderly and mature solutions. So if I have a large string of ones and zeros, a protocol is necessary to make that string into something meaningful. Here's an example of the chaos that comes with bits. Let's look at the binary string 11010. This binary string represents the number 26. This string also represents a random zip code in Long Island in New York. Though it appears 5 simple numbers, this string is terribly chaotic outside the context of a specific protocol. In short, they exist as context to make meaning out of information. And for the purpose of computers, we tend to make protocols to add meaning to strings of ones and zeros. Let's look at an example of parsing some string using a random protocol. When we enter our birthdays into our YouTube profiles, for example, we enter month, day, year. Although YouTube asks for these fields in separate text boxes that are split by dashes, when YouTube stores our birthday in its databases, it stores only the numbers and not the dashes. This saves them 2 characters of space for the billion or so records of users that they have in their database. And this ends up being an extra 2 billion or so dashes of saved space. That's not a lot, it's about 2 gigabytes, but the logic applies to bigger problems as well. Although storing numbers is beneficial, it introduces new problems. 11/21/1998 becomes 112.11998, which to a computer is simply a number around 11 million. Now that's a problem. A birthday is not 1 number, but 3, and we managed to confuse the computer. So, to combat this, let's make a protocol to solve the problem. Whenever we read a string of numbers that we know is a birthday, we will take the first 2 digits as month. Then we'll take the next 2 as day. Then the last 4 will form the year. We just made meaning out of some number by reading it under a certain protocol or context. Something that we will consistently run into with protocols, especially with communication protocols, is that there are 2 entities, one who structures the information and one who parses it. In our birthday example, the profile editing page structures the information, and the profile viewing page parses it. All this is to say that although it may seem that the ancient engineers of the internet made arbitrarily complex decisions, because that's what smart people who make the internet do, these engineers are actually practical people, and every protocol that they made served a practical function that allowed them to advance in the creation of the internet. Back to the problem. I want to get a message from computer A to computer B. What do? Well, first, and inevitably, we need some physical medium between the computers, which could be anything from a long wire across the Atlantic Ocean or some electromagnetic wave. This medium will carry our digital bits of information, the ones and zeros that we're trying to grant meaning to. This may be a shock for some of you, but long wires at the bottom of the ocean are a crucial part of the modern internet. Like I said, the engineers of the internet were practical people. There's no way to communicate between 2 things without a medium, so they created the medium, regardless of how difficult it is to make a long wire across the Atlantic. So we have a medium. The next thing we need to do is specify our target computer. We can't deliver mail without an address, and same goes for messages and computers. To do this, we should probably come up with some address protocol so that I can distinguish my computer in Albania from other computers by giving it a unique address. Our protocol will make meaning of bits by arranging them on our medium such that each quantum of information we send has an address preceding our message. You can think of these arranged bits as an envelope with an address on it and with a message inside. Just like how we had a month and then date in our birthdays, we have an address and then a message in our protocol's bits. Let's call this address protocol the Internet Protocol. or IP for short, since any device with this address will be considered to be part of our internet. Great, now we have computers that know about each other. That's a major achievement, because along with the physical medium, now we can start sending bits across a wire to a target. We technically have a functional communication network now, but assuming we have devices capable of more than one process, we're not done yet. Let's say my computer is running the Gmail process and the WhatsApp process. What if my message sent through the wire is picked up by WhatsApp instead of Gmail? Computers are powerful enough to run multiple apps, right? So our messages journey is not over yet. We need to specify which app we want to communicate with. Let's create a new protocol for that. In our protocol, let's agree that whenever we run an application, we will give it a unique address within the computer. So now we have two addresses across two layers of protocols: a computer address, an IP, and an application address. Now, when our message gets into the computer through IP, we can route the message within the computer to the correct app based on this new application address. This unique address will be known as a port, and our new simple protocol will be named UDP. It's worth referencing the birthday example again, as we use the same thought process to parse our birthday's month and then day as we are to parse a computer address followed by a UDP port. UDP on top of IP is like day on top of month. It's the same logic. And this is the beauty of computer science, because once you understand the high-level details, the devil in the details becomes a little more friendly. We did it. We're able to send messages between processes on hosts. Theoretically, we're done. But practically, leaving here would be frightening. What if we needed to send a UDP message to a friend that represents the title to 3 Ethereum tokens, but the wire in the Atlantic that's carrying this message is cut by a piranha? Well, there goes 3 tokens. We benefit from a new protocol that ensures that we know when our messages are delivered or not. We need a protocol to control the transmission of our bits. We need TCP. In our protocol, let's create a logical connection between the two computers before we send messages. As usual, we're structuring bits again. This time, we structure bits that tell us whether or not the computer receiving the bits should treat the next bits as part of the same existing connection or not. In short, we create a logical connection by using some metadata. Now, anything passed into the connection from computer A will come out the same connection on computer B reliably. Or at least we'll find out the connection couldn't go through. That was a severe oversimplification of TCP, but TCP is going to be enough for us to achieve our end goal of sending messages from A to B reliably. So far in our journey, we've reached a pivotal moment now. We've implemented the host-to-host layer of the internet. Let's put that back into perspective. This means that I can open up my computer, look through my monitor, and see information sourced from another computer. Without loss of generality, TCP is the bedrock of our applications. It, as well as its IP bedrock, enables almost everything we achieve on the internet today. And that's why you're going to see TCP over IP so often in networking. That said, we're in a state of chaos again, albeit a better chaos than earlier, because at least now we can communicate between two hosts. We've packed our digital envelopes from computer A to computer B, and now we've unpacked them and are faced with making meaning out of the chaotic string of bits that the envelope contained. What do we do to combat chaos? Well, if you've been following, we make protocols. In parallel to each other, we make independent application layer protocols, each for their own use case. We create the SSH protocol so we can securely log into another computer. We create the HTTP protocol so that we can send hypertext, like HTML pages and websites, between computers. From the point of view of TCP, we can create new application layer protocols on demand, though they likely won't be as widely renowned as major players like HTTP. For the developers watching, sometimes people or companies like MongoDB will package their protocols into code packages called drivers. A Mongo driver, for example, is code that wraps around a TCP connection and sends bits in its own custom way. I want to talk a little bit more about this thing called HTTP because it is so prominent that I, as a 4-year-old going on Disney.com, interacted with it. Now, obviously, at the time it meant nothing to me, but that's beside the point. If you're an engineer and your tech is so extensible that someone used it to make a product toward a 4-year-old, you know you've designed something impressive. HTTP is the marble glaze on top of the internet cake. It reduces communication on the entire internet to effectively 2 simple parameters: IP address and some text. It will take that text and send it to the IP address. That's all. That's really what we were talking about when we said we wanted to send a message to another computer. If I stuck with TCP alone, I'd have to manually translate my message into binary digits first. That's no fun. And guess what? If we make more protocols, like if we decide to structure our text in a specific way, known as HTML, let's say, then we can also render specific structures of text visually, and that's a website. Websites come from the same thought process that makes you understand 112319998 as a birthday instead of the number 11 million. And with that, I end my mini lecture on how the internet works. I'm sure there are a lot of you annoyed at the fact that this description was really high level, but the more you get comfortable with computer science, the more you realize that it's worth only remembering the high level details and trusting in your abilities that when you need to know the technicalities, you will be able to figure them out. Again, a lot of what's on this channel is my raw and fact-checked understanding of concepts that I have successfully been putting into practice in my job, which is not to say that it's perfect, but that it's practical enough to get by. This information is not enough for you to debug errors that may come from bugs in these protocols, but it is likely enough for you to understand how to use the protocols assuming everything is working as intended. Thank you all for watching.